Alrighty then, so today, as it says in bright pink, we're going to look at what happens when you take the derivative of logs other than base e. Okay, so other than natural logs, because now you know how to take the derivative of the natural log, it's just u prime over u. Easy peasy, lemon squeezy. However, what if it's not a natural log? What if it's, I don't know, log base 7, or log base 34, or something other than e? On the first slide, I've got a couple things. Actually, I have 4 things. That's not a couple, unless you refer to it as a couple of couples. Then that would be 4. But some things that you should know from pre-calculus. What does COB stand for? Correct. Very good, Raman. Thank you for the help. I'm so glad we're recording, so I can save that for prosperity's sake and share it with all my students in the future.
That derivative is spelled wrong?
What's it stand for?
Derivatives.
Kaylee out badgering.
Coefficient of base.
Coefficient of base, close but not quite. What would you call a bunch of quarters?
Quarters.
Sense.
Change.
Change of base.
Change of base. Very good. That's a change of base form. So anytime you have a log that's not a natural log, you can make it a natural log by just doing that business. However, it doesn't have to be a natural log. If you have a log base 7 and you'd like it to be log base 2 for some weird reason, I don't know why, then you can just change the natural logs to log base whatever. Log base 7, log base 2. Okay, but most commonly, we'll use a change of base to convert to natural logs because natural logs are funner. Okay? Any problems with any of those? You should have, knock on wood, seen those before, but they will pop up occasionally. And in fact, we've been using some of those already. Notice in the first one, numero uno, in the exponent there, we can use the log properties by putting that x back as an exponent, so you get e to the natural log of a to the x, and e to the natural log of anything is just that anything, and then everything else goes from there. Okay, we good? Got those? Any problems? Beautiful. Next slide. Should be blank. It is. We're going to break this into 2 days. The first day we're going to do derivatives. The second day we're going to do integrals. Integrals and derivatives of things other than log base e. But before that, we need to do a little bit of pre-calc review here and ask a simple question. How would you solve that? Q-tip boy.
Well, 2 to the negative 6 equals x.
Say again, I'm sorry.
2 to the negative 6 equals x.
Beautiful. Converting between exponential and logarithmic. The base of the log becomes the base of the exponent raised to the power on the other side of the equal sign, 2 to the negative x. Sorry, that's a 6. 2 to the negative 6 equals x. If you don't have it, get out your calculator, please. And tell me what 2 to the negative 6 is.
A small number.
It is a small number. And this is a number that you should be able to do without a calculator, but we'll do it with a calculator just for giggles.
64.
1 over 64 is correct. 2 to the negative power is the same thing as 1 over 2 to the 6. 2, 4, 8, 16, 32, 64. Any problems? No? Outstanding. Easy peasy lemon squeezy, right? Great. Let's take some derivatives then, huh? What if I want to take, we'll put this over here in its own corner. Go over there. Think about what you've done. And we'll switch to light blue. If I want to take the derivative of a to the u. Okay. So a is not e. And u is some function, and that function could be something as simple as x. It could be something as complicated as a rational function involving multiple x's and all that other fun stuff. You get a nice little formula here. A to the u times the natural log of a times du dx. How is that different than e to the u? Well, the only thing that's different there is obviously instead of an e you have an a, but we're including the natural log of a in that case. You got to take the natural log of that base. What is du over dx also known as?
The derivative of the exponent.
Also known as? If it was a to the x, would there be a du dx there?
Oh, no.
Oh, implicit. Yeah, implicit.
Nope.
Chain.
It's a chain, correct. Just a chain rule. Just like when you're taking a derivative of e to the x, or I'm sorry, e to the u, it's e to the u itself. E to the u times the derivative. Yes? No? Miss?
What was it?
Bummer. Got to remember to chain on the derivative of the function up on top. Okay? Now, I would like to say that you're going to memorize this or you're going to learn this through multiple practices, but this is probably a flashcard thing. It should be on a flashcard somewhere so you remember how it goes. And it gets a little confusing that we start looking around at derivatives of e to the u and then derivatives of a to the u and remembering all the components that go along with that. Next one. Whoops. Log base a. This one's a little trickier. We already know the derivative of the natural log of x. That's just 1 over x. If it's not a natural log, log base a, then we get that monstrosity. And yes, that u is supposed to be in the denominator, along with the natural log of a. Again, flashcard is probably the best way to approach that.
Yeah, let me get my janitorial back.
Questions? I mean, I don't know what questions you would have, but how could we make it more interesting?
Absolute value.
Absolute value would be good. The absolute value of a trig function would be great.
Square root.
Square root of an absolute value of a trig function? Good. Anything else?
I'm sure there is, but like.
Integral.
Like how bad do you want it? Yeah, how many times do you want to get punched in the face? That is more than once or twice. It's just a waste of time. Yeah, I don't have any of those for you today, sorry. I just have some straightforward problems. Let's try something like the following. Okay, figure out what F prime is. Now, I understand you just learned the formula, or you just saw the formula, so you're not going to have it memorized. But eventually you're going to be identifying each part of those things. So if you go back, or if I go back a slide, I'm taking the derivative of a function raised to an exponent. So this is an a to the u. Question you might want to ask yourself is, what's a and what's u? In this problem, what's a? 12. What's u? Plus 3x squared. Take that stuff and apply the formula. Ellery, what do you got?
I got 12 raised to 6 plus 3x squared
Its own derivative times.
times natural log 12 times 6x.
Okay. That's Spanish for what? Okay. Sarah Blue?
I thought it was 1/6x.
9. 9. Oh. 8. Question over there.
Yeah, if you want, can you simplify that more into 72x, because they have to stay different, like the natural log of 72x, or is it like 6x natural log of 12? No?
Put them in parentheses. Those two don't play well together.
Oh,
Okay, so don't spend too much time trying to simplify it, especially a problem like this where you can't simplify. Okay. So again, is this difficult? No, it is if you don't know the formula. So somewhere along the process, you got to learn the formula. Okay. So now, if we wanted to make it more interesting, we could include trig, we could include absolute value, we could do all that, but I'm not going to do that. I'm just going to ask you a simple question in a lovely shade of
Pink, purple.
I bet teal.
Yeah,
Yellow.
we'll go for
bright green.
Yeah, that's that one.
This one? Find the equation of the tangent line to the function
I think it's 13.
Okay, doke. So to make it more interesting, instead of just asking for a derivative, let's find the equation of a tangent line. What are the two things you need for the equation of a tangent line? Sorry, hold on. What are the two things you need for the equation of a line? Slope and point. Do you know the slope?
No.
Nope, probably gonna find that. Do you have the point?
Yes.
Yes. Sometimes you won't be given the complete point. You might just be given the x value or the y value. In this case, I was feeling generous today and I gave you the entire point. You're welcome. Go find the slope, put it together in the equation of a line. Do not try to simplify it. Leave it in point slope form. Don't get too fancies in your pansies. What's A in this case? 3. What's U? X. You are not expected to know the values of natural log functions off the top of your head. So therefore, you would answer with a form for the natural log.
Yeah. I have it, no one. It's kind of just like, it gets a little forward, the bottom, you just drag out.
That's the general equation of the slope. We know the slope at that point.
Wait, so the slope has to check back on those. No.
Come on.
I don't think I have.
Yes, you do.
Well, let me consult with my teammates.
Come on.
Is that what you got, kids?
You got this.
What happened?
My notebook hit it and it erased it.
Don't do that.
Plug in.
How do you do? Any problems? Anything that's not perfect about that? Notice, he takes a derivative to get 1 over the natural log of 3 times x times 1. Where did the 1 come from, Tim?
The derivative of u,
Right.
which is x.
Good. So he's getting all fancies in his pantsies and including the derivative of x, which we all know is 1. Well done. That's the general equation for the slope of at any point anywhere on that graph. However, we're looking for the slope at the point 27.3, so we plugged in 27 and got that. Okay, we good? Any problems? Yes, it's just that easy. Okay. Now again, the difficulty is not in the application, it's in remembering all these formulas as these things get thrown at you. Okay, doke. Let me stop the recording, and then we will